Okay, so in this course, we've been talking a lot about modeling. So how do we model motion and how do we model the forces? Um, so this is just a method of how do we really represent energy. So it's just another model of how we look at energy, right? So a common way to look at energy, right, is to simply use just a pie chart, right? So if you just kind of think about when you were growing up and learning about pie charts, you know, the circle, right, represents the whole, right? So everything that's happening. So with regards to energy, right, the whole would be the total or the mechanical energy, right? While the slices of pie represent the pieces, right, that make up that circle, right? For energy, you're going to have, for what we're focusing on here in physics, okay, you're going to have three things, okay, for the most part, right? So you're going to have a kinetic energy, you're going to have potential energy, now that could be UG or US, again, based on what's happening, and then you're going to have what we're going to call internal energy, right? So this is just, internal energy is going to be essentially anything that comes like from heat, from friction, okay? The internal energy is just what we consider to be the sum of all those non-conservative forces acting, right? So this is like the sum of all that work done by those non-conservative forces, okay? So remember, I readjusted this page, okay? I started with the harder ones, and then I went back and added in a couple of the simple ones, all right? So the first example we have a book sliding across the table, okay? And what we're going to do is essentially we're going to take a snapshot at three positions, right? And so here's my book, right, on the table. I'm going to take it at three positions. One at the beginning, one in the middle, okay, then one at the end, okay? And then the thing about the end is that it comes to a stop, right? And so our system is the book and the table, right? Because if you don't have those two as your system, these become a little bit more difficult. You'll see when we do the last two examples, okay? So at the beginning, now note, you could include potential energy here, but again, we're going to say our 0 point is the table, okay? So H equals 0 is the table, which really just eliminates any effect of potential energy. So at the beginning, it's going to be all kinetic, right? The internal energy, the friction has not taken effect yet, okay? Now about halfway, the good thing about energy is that it is proportional. So we're going to have about half kinetic energy, half internal energy, all right? And then when we get to the end, right, it's come to a stop, which means, right, we have no kinetic energy because V equals 0, which means all that kinetic energy has been transferred to internal energy, all right? Now, if we look at the next one, we're going to have a box, sorry about that. We're going to have a box sliding down a hill, okay, and then coming to rest. So we're going to assume that this whole surface is friction, right? So we're going to have some sort of friction involved with this whole surface, which means at some, for each diagram, right, we're going to have some sort of internal energy, okay? So we're going to do three positions again. So here's position one, right? At position one, a little piece of it is internal energy, but the majority of it is gravitational potential energy, right? Because we're up a height. And we're going to say H equals 0 is down here, so here we're up a height. At position two, right, what you're going to see is that all that potential is now being converted to kinetic, okay? But we do have, in fact, hold on, I messed this up a little bit. Okay, it's actually going to be a 50-50 split, and I apologize for that. Okay, but again, you're going to see, because this is going to be a friction surface, you're going to have this internal energy, okay? About halfway or down at the bottom, the transition area, right? All that potential that we've had has now been converted to kinetic, but again, we still have this friction surface, so we're still going to have this internal energy. And then it's going to come to rest, right, at position 3, which means all that energy is now being converted to internal energy, okay? Um, okay, the next example, we have a frisbee being thrown up, and it's going to land in a tree. Okay, so we just kind of sketch out our physical situation. All right, so where we release it, we're going to call h equals 0. Okay, it's going to land up here in the tree where it's not going to be moving anymore. And we'll just pick a point in between. We'll say halfway of where we'll look at it as well. Okay, where it'll be up a distance, but also still traveling on its way up to the tree. Right? So here's our first one. Remember, the circle will represent the total energy, which in this case will be set by how fast we're throwing the object up. So at the bottom, it'll be all kinetic energy. And we'll look at that point halfway because it's very easy to spot because it'll be half kinetic, half potential. Okay? And then again, it'll be 50-50. It'll be 1/2 mv squared plus mgh, but all that will equal the k from the beginning. And then we will look at it at the top when it stops moving, which means now we're up a height, okay, and it's not moving, so all of our energy has been converted to potential energy. Okay, so these 3 examples tended to be a little bit easier because we're not really introducing or taking away energy of the system. The next 2 examples will start that kind of transition or start talking about what happens when there's work done on the system, okay? And we'll look at an example where it's positive work, and then we'll look at an example when it's negative work, right? So the first example says a train at rest, so our train begins at rest is what it should say. Superman's going to push the train. Again, we're starting out from rest, giving the train a constant acceleration. And then consider the situation during the time that Superman is pushing the train only. All right, and so part A, make energy pie charts for this situation when everything is in your system. So if I have my train, right, and then I have Superman over here pushing, okay, the first scenario, part A, says, okay, everything is the system, which means Superman's energy, or what he's doing is internal. Okay, the friction on the cart or on the wheels is internal, okay, and so this ends up looking very much like the pie charts from before, okay? Now, the difference will be we're going to take that internal energy to begin with, right? And then we're going to slowly start converting that, okay, which these circles really should be the same size. We're going to start converting that to kinetic because we're starting from rest, but you remember, to get this train to move, you have to overcome friction, which means there's internal energy. And then once we get it moving, right, constant acceleration, all this stuff is now equal, which means all that internal energy now has been converted to kinetic. Now, we chose a point where it's just a little bit of kinetic. You can also choose a point where it's like halfway down, where it ends up being a 50-50 split, okay? Now, the next one is make energy pie charts for the situation. I completely, messed this sentence up. So make energy pie charts for the situation if the train, right, is the only object in your system, okay? And so the way this begins is, so if we draw our Superman train picture again, so here's Superman pushing. So the only thing that we're going to look at here is the train, which means now Superman's push now becomes external. So the way we look at it is that the train is not moving to start. And we're going to put just a little dot there to show that there's something happening or about to happen, okay? But one thing you'll notice is that dot's going to grow, okay? Because what Superman's doing is he is introducing in energy to the system, right? And so we'll have a little bit of kinetic energy the next time. And then when we finally get here all the way to the end, we'll have more kinetic energy as we travel down the track, okay? Again, this is, when you think about this, this is Superman, and the reason why the circle is growing is because Superman is actually introducing in energy, right? In fact, I forgot to add a couple things here. So there will be a little bit of internal energy. Um, in fact, it should be about the same in terms of its proportion. Okay, so there's internal energy here. Okay, and this little piece here is internal energy as well. Okay, but the reason why this circle is growing is because now the system is no longer, if you want to say, isolated, which means conservation energy is off. So Superman, right, is increasing the energy, right, because he's doing work. Okay, so he's increasing the energy of the system, right? And if you remember, if Superman does work, it changes the kinetic energy. He's doing positive work, which means our delta K ends up being a positive as well, right? The next example, what happens now if Superman decides to stop a train, right? This is a runaway train going down track. Okay, so now the train is speeding down track with a constant velocity. Superman gets in front of the train and slows the train to a stop. Consider the situation from the time Superman starts slowing down until the train comes to a stop. And the train is the only object in our system, right? So it's the kind of reverse of what we were just doing, right? And so train's speeding down the track. We have Superman here. And I'm going to draw him sitting down. He's trying to stop it, okay? And he's going to do a force, right, in the opposite direction, okay? Which means as he starts the stopping process, so we'll have a little bit of internal energy, but most of it will be kinetic. And then now what he's doing is no longer, he's not bringing energy into the system, he's actually removing energy. All right, so we'll still have this little piece of internal energy, okay? And you can see the system is growing or shrinking, and finally until you get to the end, when it's not moving anymore, because Superman has saved the day and he has stopped that runaway train, okay? So this example is the opposite of the previous one. Now here Superman, right, is decreasing the system, or decreasing the energy in the system. So he's doing work, but he's doing negative work, okay? And so if we kind of do our relation that we just did above, so what's happening is that if he's doing negative work, our change in kinetic energy will also be negative, okay? So there's the decrease in the system. So we have one more thing to do in this unit, and it says talk about power, and then we'll start focusing on